So, our next keynote, that was really fantastic. The break, the energy, the discussions. It's brilliant to see us all having such inspiring times. So next up, we have got a keynote, online keynote, and this is coming from Irina Rish. Irina is an associate professor in the Computer Science and Operations Department at the University of Montreal. She holds 64 patents, has published over 80 research papers in peer-reviewed conferences and journals, several book chapters, 3 edited books, and a monograph on sparse modeling. Please give a warm welcome to Irina Rish online on scaling laws, emergent behaviors, and AI democratization efforts. Thank you.
Hi, can you hear me well?
Yes, we can hear you and we can see you.
Okay, great. Okay. Well, thank you so much for inviting me. Thank you for kind introduction. I'm really sorry I couldn't be there due to some scheduling constraints, but I'm happy to be here virtually. And indeed, let me share my screen. Just a second. Okay. So just go to there. Okay. Okay, can you see my screen now? Okay, I see that you can see my screen. It's been projected well, right? Okay. Perfect. Okay, so indeed, let me start briefly with this kind of high-level overview of several topics that probably deserve separate talks on their own. And yes, talking about AGI, we will be actually talking about the most recent kind of advances in large-scale models and scaling laws that many people believe promise to bring us closer to AGI. Interesting behaviors on the way, and also practical issues about how can we train those models if we're in academia or open source communities and compute gap between us and industry is widening. So I'll try to cover all 3 topics that we've been kind of involved in the last 2.5 years, I would say. Okay, so yeah, this is AGI conference. So let's start with the AGI slide, and I probably don't have to repeat it, but we all know that everyone has somewhat different definitions of AGI, and that causes usually sometimes even heated discussions on Twitter. But yeah, to be serious, indeed, it's a notion that indeed different people and different groups define in particular ways. And I will probably just follow somewhat less mysterious definition, which has no necessarily consciousness on that or anything like that, but essentially as practical as possible definition, kind of following what OpenAI put on their webpage a while ago, that essentially you want a system that similarly to human is capable of doing not only really well one particular task like it used to be in narrow AI, but it really should be able to acquire and remember a huge variety of different skills over its kind of lifetime, just like humans do. We can require the performance be kind of near human level or at human level, or kind of better than human, but that's kind of more of a detail. So essentially the definition is in some sense more kind of mundane and practical than maybe some people imagine AGI to be. So it's essentially a highly multitask system, or as again, OpenAI would say, highly autonomous system that outperforms human at most economically valuable work. Essentially multitasking where tasks are useful. So if we think about that, like one step back, or I don't know, multiple decades back, what was always the key driving kind of objective of statistics, machine learning, and artificial intelligence lately that kind of was mainly dominated by machine learning goals? It was always generalization, starting with very classical regression where you have a bunch of points supposedly coming from some data distribution, and you want to extrapolate to unseen points, you want to generalize, still assuming that the data come from the same distribution, the IID, all the good old stuff. The next step was, okay, let's push generalization to a bit more, well, general level. So out of distribution generalization was and remains kind of a really hot topic in machine learning and deep learning particularly. We really would like to have systems that are kind of robust rather than brittle to changes in data distribution and can generalize maybe zero shot or few shot. And that closely relates to many other overlapping areas of machine learning and AI, transfer learning, continual learning, meta learning. Settings change, but the key goal is you want to improve the ability of the system to generalize to novel situations and novel tasks, and be able to transfer and abstract their knowledge so that they are capable of doing something reasonable with tasks and data that are very, very far, ideally, from the distribution they were trained on. And recently, literally in the last 2-3 years, we've all been witnessing what some call neural scaling revolution, which kind of makes a huge step in the direction of generalization, and we'll talk about that. But many of you already know that all these large-scale pre-trained systems, with GPT-4 being one of the recent examples, and also many generative systems like Clip, DALL-E, Stable Diffusion, and so on, taking the world by storm and precisely impressing everyone with their generalization abilities, or kind of ability to facilitate generalization on top of them. And indeed, what's going on seemed to be resonating well with a bitter lesson by Rich Sutton, which was essentially talking about previous kind of patterns in development of AI over like last 70 years. Essentially, you start with some specific human knowledge that you put in the system, like rule-based expert systems, say playing chess and putting all their human knowledge in their ontologies and so on and so forth. In a few decades, you have much more compute, much more data, and you have a much more general, rather than kind of specific to this domain methods like massive search that kind of outperform all these systems developed with a lot of human knowledge and inductive biases. And examples keep going on, like chess was just one, well, AlphaGo and so on. So basically the whole deep learning was example of that trend. So you go from kind of handmade features designed for each particular domain, say in vision or language and so on, you go to generic kind of methods like generic architectures in deep nets, extracting those features automatically and utilizing massive compute and massive data that became available. So essentially, that same kind of pattern keeps repeating itself in multiple areas that used to be kind of addressed in machine learning by expert knowledge and kind of developing particular methods, inductive biases, features, and so on and so forth. So what we kind of learned from that and where we're going with that seems to be that we're trying to even further generalize what part of the human knowledge we actually want to put in the system. We don't want to really put too much detail about how we think. We want to build systems that are able to develop those thinking abilities. And we want to make them as simple as possible, as general as possible, but probably not simpler, as Einstein would say. And we would like to utilize basically their scaling properties to see if they can develop the abilities of interest. And that's what we've been kind of witnessing, as all of you know, in the past couple of years, essentially starting with, I guess, GPT-3 in 2020 and neural scaling laws that appeared in like late 2019, early 2020. And since then, there was like exponential growth of this field. That's now the term was coined by Stanford paper, foundation models. So by foundation models, we mean all this very large scale, pre-trained on huge amounts of data in unsupervised way. So they kind of just absorb knowledge, they absorb the probability distribution of data, for example, language. They absorb language patterns by being trained over like tons of data from the whole internet. And they can serve as foundation for building whatever applications on top of them. And just as foundation, they are not only kind of the basis, but they also not yet fully there. You need to build stuff on top of them. Maybe you need to fine tune them and so on. But that's kind of the reason behind calling those system foundation models. So yeah, the history kind of develops as we speak, because there are many models, especially open source models, kind of being trained practically and kind of released almost every day these days. So GPT-3 kind of started the trend, with claim to fame being that on totally new data, new tasks, you actually can adapt and do quite well in few shot manner. So here goes your out of distribution generalization, or basically adaptation to new domains, your transfer. So those systems essentially didn't change much in terms of architecture as compared to their predecessors. They changed in scale. And apparently, the scale of the data, the diversity of the data, combined with capacity of the model, the scale of the model, allowed them to become really good few-shot generalization kind of agents without any particular details built in specifically or any specific algorithms developed for that. So, and the story goes on with multimodal systems, not just language systems, like clip followed, image to text, zero-shot generalization, pretty much on out of distribution image domains, beating state of art, and DALL-E, image generation, and then many other systems, well, stable diffusion and so on, code generation, and most recent, of course, GPT-4, which is now part of ChatGPT, and the whole family of open large-scale models and open data sets. I will talk about the open source a bit later, but like Llama was one of them. And essentially the recent trend is scaling data even more than scaling the model size, which kind of a good news for people who have relatively limited compute and would like to train state-of-art models. What was interesting about the systems was not just kind of the great engineering that went into them, but also the interesting empirical science, almost like physics of AI, about how this behavior of the system can be actually predicted empirically based on so-called scaling laws, neural scaling laws, which also kind of took the field by storm because they were quite simple and quite useful. And many of you probably have seen that paper by Jared Kaplan and his collaborators from OpenAI. And basically, those straight lines on the log-log plot. So essentially that meant that behavior such as test laws, but also many other properties of the systems, I will talk about that soon, they can be described by relatively simple things such as the scaling laws, the power laws. So essentially the power law in a log-log plot is a straight line, and you only need to feed a couple of parameters. And apparently on multiple orders of magnitude, you can predict how the performance of those systems, in this case it was GPT-3, will behave as you increase amount of compute available, data set size, and the number of parameters, the size of the system. So those plots essentially were derived by Jared and collaborators and helped them to kind of steer development of, say, GPT-3 in desirable directions, because basically you can predict among multiple kind of choices that you can take, whether it's hyperparameters or other kind of decisions you need to kind of take when you scaling your system, which decision will be most promising and will give you the best performance if you allow it to use more compute. So the plots essentially mean if you increase compute on the leftmost plot, for example, and for each particular amount of compute available, you allow your data and parameters kind of be whatever you need to get the best result. So basically you try multiple combinations and choose best result. Then the improvements with increasing compute will follow power law with this particular parameters as in the neural scaling laws paper. Similar with different parameters behavior, also power law, happens when the data grow while compute and number of parameters is unconstrained or unbottlenecked. So essentially you can choose the best. And again, similar behavior, just with different parameters, happens when the model size grows, and you can choose whatever amount of data you need and amount of compute to get the best kind of performance for given model size. So that was a classical set of scaling laws that essentially were brought to people's attention in 2020. And since then, there was an explosion of papers trying to study scaling laws of different behaviors in different settings for different architectures and so on and so forth. And the reason the scaling laws are kind of not just academic curiosity, like we would like to know how does this system will behave, it's in a sense can be viewed as a very practical kind of investment tool for choosing which methods to select and to invest kind of your compute resources into. And classical example, one of many, was a comparison of convolutional networks that up to like 2020, 2021 were considered state of art in kind of image processing, and they're still kind of pretty good. But it was interesting that more generic method, vision transformers, which pretty much uses architectures that has no specific inductive biases that convnets use, was not maybe as good as convnets when the data were relatively small, like say 10 million or 30 million is small, but when the data grow by orders of magnitude, apparently the situation reverses, and you see that vision transformers start to outperform the more specific kind of vision specific convolutional networks. So this is a classical example of kind of bitter lesson as well. So you may invest time into designing specific architectures with specific inductive biases that work best at low scale, but as more compute and data become available, more generic, maybe simpler, non-domain specific methods that also scale well may outperform your specific ones. So this is kind of classical example where scaling laws allow you to see the full picture, and that's why they're important. And if you think about that, why they're important, indeed, you can think about multiple paths to AGI. But perhaps, as usual, in nature and in kind of science and economics, the fastest path matters because essentially that's what kind of going to lead to the goal, and that's what kind of others are more likely to follow, because kind of what exists persists. What is most successful and keeps getting us to the goal faster, that probably will be the path we will choose. Although perhaps there are many, many alternatives, but if they don't scale as well, then the fastest scaling one will win. So again, it would be nice to estimate scaling laws of whatever approaches we're trying. So usually, what can we evaluate given particular methods, architectures, and so on and so forth? We would like to kind of see how not just performance on all possible downstream evaluations, but also other properties such as, for example, alignment, which could involve multiple kind of useful things like truthfulness and so on, but essentially alignment is yet another not very precisely defined term, just like as AGI, which roughly means that behavior of the system may be hard to describe in optimization function, but we want to be able to kind of to steer it to something that will not contradict our intentions and values. And we'll talk about that a little bit later. While at the x-axis, we would like to plot whatever kind of quantity our approach can be bottlenecked by, like what is a resource that might be limited, which is usually compute or say amounts of data. So that's what kind of scaling laws are about, but they kind of started a while ago. It's interesting that people looked into them, but only recently with large compute that really became available and amounts of data, they became also practical. So actually, it's interesting that I think one of the first scaling laws papers was the old one from New Reeps 1994 by Irina and her famous co-authors, including Vladimir Vapnik. And the interesting thing is it was also kind of study of neural network behavior, error in that case, basically log error, and they also observed power laws behavior as a function on the x-axis of dataset size. So those straight lines were not invented by Jared Kaplan, but they've been around for a while, even particularly in the domain of neural networks. And well, forwarding all the way to the 2017, another paper by Joel Hasnes and co-authors expanded basically this observation by orders of magnitude, also showing how the scaling laws kind of follow the power law straight line in the kind of middle region, but there could be also regions of slow improvement in the very beginning, say when the data set size is way too small for the model to learn anything kind of useful, so the performance does not improve that fast. And then there is kind of slight break in the pattern where we get into this power law region. And at the end, far kind of in the future with like large amount of data that pretty much may cover the whole distribution of what's out there, the model behavior performance will kind of asymptote. So this was kind of also a hint of what you can observe in terms of several regimes of kind of different behaviors connected by the breaks. And I'll talk about that very soon when we will kind of fast forward to the most recent developments in neural scaling laws. Anyway, so I just kind of wanted to say that the individual observations of scaling laws as a function of data, or in this case, the more recent paper, 2019, it was at ICLEAR and also was dissertation of Jonathan Rosenfeld. it observed power law dependence on the model size, on the number of parameters. And then we have Jared Kaplan's paper, which kind of also observed and confirmed both data and model dependent scaling laws, and also added on top of them the scaling law as a function of the compute. There was also many more recent developments. There were, I kind of not showing it here, but there were more efficient scaling laws, also power laws, so-called chinchilla scaling laws, which improved over Jared Kaplan's. But then there was another interesting observation, like besides all these straight lines for the kind of laws, test laws, there are other metrics of performance, especially those that depend on particular downstream tasks. Well, downstream task is basically what you do after you pre-train your model, and you may provide it with kind of prompt asking to make some kind of inference and reply to this prompt and language tasks, or you can perhaps fine-tune, you can do various things kind of downstream. So this plot from the original GPT-3 paper was interesting because unlike other tasks and unlike the test laws, it was a kind of problem where the system was supposed to answer arithmetic questions like 2-digit addition, subtraction, up to like 5-digit addition and subtraction. And what was interesting is that there was a clear kind of sharp transition in the quality of the answers, in the accuracy at particular size of the system. So there was almost like up to a certain size system was unable to grok or capture the task, say, of 2-digit addition, but then at 6.7, it started getting better. For the more difficult tasks, this transition happened later at larger system size, but that was kind of interesting plot that started this whole kind of investigation of what can happen in terms of performance on particular tasks changing abruptly in almost looking like phase transitions in physics. Well, I will kind of not claim and not call them necessarily phase transitions. I would rather say it's quote unquote phase transitions, because yeah, phase transitions in physics have particular properties, and unless we kind of make a one-to-one correspondence between what's going on in the neural net and the situations, we kind of should be more careful with terminology, especially if there are physicists in the room. But talking about sharp changes in the scaling behavior as a function of particular kind of parameters on x-axis. Another paper, also a couple of years ago, observed the sharp, rapid change improvement in accuracy as a function of compute in specific setting, again, of like similar to arithmetic type of problem. So it was like a arithmetic model or model or something. I don't remember in the exact details. The point is that the model was being trained on some kind of large table describing the operation. It was a binary operation. The part of the kind of table was given as training data, the rest as test data, and the task was to kind of learn the operation, and the performance was nearly zero until at some point the solution that actually was nearly perfect was found, and the performance was improving very sharply, first on training data and then on kind of validation on test data. So that behavior was called grokking, because the system suddenly kind of groks the task. Somewhat similar kind of sharp transitions were also on the same task observed as a function of amount of data, training data given to the system. But then people started exploring various other settings, problems, and systems, and there was this paper on emergent abilities of large language models, basically showing many situations where such nonlinear kind of performance improvement can happen at scale. So the question was, how do we capture all these non-trivial scaling laws that now go way beyond just the straight lines and log-log plots, basically beyond power laws. So recently we had this paper at ICLEAR with two of my students, Irina and Kshitish, and with a collaborator, with David Kruger, who previously actually also was a student at Mila. And the paper basically was trying to come up with a functional form that would generalize power laws and try to kind of one functional form to rule them all. Essentially, this functional form apparently was used before in different sciences, for example, astrophysics, and I guess that's how we found it. So essentially, it kind of describes a combination of power law regions that smoothly connected by those kind of smooth breaks of different kind of sharpness. The sharpness is controlled by parameters of that functional form, as well as the slopes of this kind of power laws and so on. So essentially, it's an interesting generalization which happened to be extremely generic, and indeed seems like so far one functional form to rule them all. So in the past year, essentially Ethan and Kshitish, they tried a wide variety of different settings, like trying to predict zero shot, prompted, fine-tuned, both downstream and upstream performances. The set of tasks is pretty much covering all that is in the current literature. Essentially, they were just kind of taking the recent papers with all this like foundation models and their performance shown there, and trying to see if that performance can be described by a particular incarnation of the broken neural scaling laws. And it seems like it works quite well on everything from like language, vision, audio, video, on diffusion models. And it not only works on performance, it also works on the metrics for AI alignment. I'll show a few examples. So far, it seems to be really quite generic approach to modeling neural scaling laws. Architectures vary. It's not just kind of transformers. It also works for ResNet and MLP mixer and a bunch of other architectures. It also like works for mixture of experts, for pruned models, for sparsity. And on x-axis is not just data or compute or the model size, but it could be also some other things like context size and so on, and even upstream performance. And the interesting things that you can kind of predict with that, again, go beyond just prediction error or cross-entropy loss. There are various scores that people use in different tasks that make sense there. And it can also apply to like reward and reinforcement learning and so on. So we're not going to go into all the details, but that's kind of the set of previously proposed functional forms, starting from the simple power law, it's like M2 here, with two more sophisticated modifications of that were designed by a couple of papers last year, precisely to try and cover wider range of behaviors. But this is just kind of one example. Like in the table, I'll show many examples in particular plots. It seems that none of those functional forms, even those two kind of more sophisticated, can cover the whole range of behavior and can be as accurate as this broken neural scaling laws, which kind of outperforms them on pretty much all these tasks. And unlike those, it can cover situations such as like inflection points or transitions, and it also can cover even non-monotonic, say, generalization, like basically generalization curves can have multiple bumps and so on. So it seems to be well covered by this functional form, not so well covered by anything that was proposed previously. So now we're going to see a bunch of examples just to kind of get some feel of how it works on wide variety of tasks. And essentially, what we have here, so basically we'll have black points, which are the data, say, given, well, training data, or the data we fit in the model of this broken neural scaling laws, and then the green points are prediction. Yeah, and actually, okay, so the red line is broken neural scaling laws that was fit to those black points, and then the green is basically what we predicted. So here, essentially, we have example of double descent, non-monotonic curve, and based on the black points on the history, we predict how it's going to kind of develop in the future. The green points, there is a inflection point situation that I mentioned. This is, of course, I mean, it's not a magical approach that can predict this very small number of points far from transition. It has to have kind of large enough set of data or kind of examples of behavior before the transition, and it should be close enough to the transition. Also, it depends on how sharp the transition is. So essentially, there are limitations to this method, obviously, but the fact that at least it's in principle is capable of such prediction is not something that we had available with those functional forms people were proposing before. So it predicts behaviors in kind of multiple orders of magnitude ahead of time. It predicts it for example, models that are also sparse, like pruned models and so on. Just many other examples like distillation, for example, not just pruning. What else? So the diffusion models, not just like language models, but yeah, basically generative models of image. Just some examples. I mean, there is much more in the paper, and basically all these cases covered in the appendix. But also interesting that metrics from like AI alignment papers also follow broken neural scaling laws, and so were also the reinforcement learning kind of metrics in some other recent kind of papers. Anyway, so it kind of works for various modalities, for various tasks. It works also for kind of coding, not just like images and language and so on and so forth. So there are many other examples with audio, video data. Basically what I'm trying to say, it seems like it's quite useful, practical, generic functional form that seems like we found that might be even kind of describing even much wider variety of the behaviors that we previously tried. So at least it's something which is, I think, a big step forward beyond the straight lines on the log-log plot that were unable to capture those interesting kind of emergent behaviors and so on and so forth. Okay. This is interesting and great, but it's all more kind of observational and theoretical. And when we actually want to, in practice, train those models, how do we go about that, especially if we don't have compute available to companies like OpenAI or Anthropic? So what do we do regarding the compute? Because it seems like the straightforward brute force kind of compute leads to such huge improvement in the generalization performance. So how do we possibly democratize AI in a sense, how people in academia and say open source communities can train such models? And one way that we considered was to kind of apply for the compute on government sponsored supercomputers. For example, Summit and Frontier are two supercomputers currently hosted at Oak Ridge facility in US. And of course, I mean, there are multiple other supercomputers in different countries and kind of more being built. So it's one possible path to kind of providing academia and open source with at least much larger compute that they had available before. Perhaps it might not still catch up with the amount of compute that companies have, but it definitely gives you ability to build things that you were not able to build before. And also, we thought that perhaps we could follow the path of the LHC collaboration in physics, basically a high energy physicist building large collaborations, applying for the large compute grants, and together trying to solve those difficult problems. So we kind of joined forces with several other groups interested in open source development. For example, Lion, the nonprofit, well known right now for building, for first of all, open source data sets, Lion 5 billion and more coming, and building better version of CLIP than the original OpenAI kind of CLIP using this new data, and many more other recent projects. And Julie Center, where some of the Lion kind of members are. Also the open source community, basically Discord community, Luther AI, that created several kind of open source models that many other things are built upon right now, such as GPT NeoX code base that not only us, but practically many other open source projects actively use right now. There are also multiple other communities, and this is very incomplete kind of picture, and more kind of joining forces recently. So we're trying to kind of grow those communities and also jointly apply for compute in multiple countries, not just for the kind of US Compute Summit and Frontier. So this was our kind of last year project, last year proposal that was accepted, and we kind of received basically close to 6 million GPU hours on Summit that we currently kind of using for some language and some multimodal kind of model building. There are also interesting projects on trying to generalize to other modalities like time series. And in general, the ultimate goal is, of course, foundation models that are capable of working with a wide range of modalities, including not just text and images, but audio, video, time series, decision sequences, such as like in decision transformers, and making those models interactive, essentially creating something we can call open chat X, where X is a highly multimodal generalist agent. So most recent kind of success story was training jointly with Stanford Research for Foundation Models and multiple other collaborators, and a company together that's kind of was founded by Percy Young and others at Stanford Center for Foundation Models, also ETH Zurich. So in collaboration with them on Summit, we basically built the medium-size open source models that essentially try to reproduce Meta's Llama, kind of recent medium-size suite of models that perform quite well and actually on par with much larger previous language models, due to the fact that the amount of data they trained on is considerably larger and more diverse than the data, for example, the previous large models were trained on. So the trend of reducing model sizes, well, reducing still to something like 7 billion, maybe 20, 60 billion, but not necessarily kind of 175, 76 billion like the GPT-3 and predecessors, but increasing the amount of data more than increasing the size of the model seems to be still promising direction, and people kind of coming up with very good medium-sized models. So this was one of them. And at that moment when we released it, it actually was state-of-the-art using particular benchmark like Helm, and it was outperforming other 7 billion versions of language models available kind of on the market. Well, basically comparing to other also open source models of similar size. And part of the effort was, of course, it always goes hand in hand, releasing large data sets. So anyone can also use them to build their models. So actually Meta might now fully release their llama model, so it will be a larger family of llamas. The previous kind of release was non-commercial, so you couldn't build anything on top of those. That's why there was so much activity trying to reproduce Meta's llama or improve over that. So this is just kind of one example. Another example is we're trying to build those interactive models that are, for example, able to take image and text as an input and produce text. We started with now somewhat older system called Magma, which was publicly available, trying to improve it. And besides just scaling to improve it, kind of capabilities of generating more meaningful and interesting text, we're also trying to focus on making sure that the models are indeed aligned with our kind of values and notion of like what the ethical response would be. And they do not answer questions, do I help old lady crossing the road, like the earlier kind of small version was answering. So that was that original Magma. And when we realized there are quite a few situations when it can give this questionable answers, we basically, besides scaling that system on Summit, we also try to kind of fine tune it with human feedback, and essentially try to steer its behavior with actually a relatively small number of good examples. It apparently suffices to change behavior into desired direction, but it's still quite open research question. As you know, the AI alignment in general is far from being solved, and perhaps is becoming one of the most active areas of research in kind of large-scale models. So there are various speculations whether capabilities of the model versus alignment are contradicting each other, and whether increase in capabilities has to lead to decrease in alignment, or perhaps you can accelerate development of capabilities while also accelerating improving alignment. I'm more of an optimist, and I think that the latter situation is quite plausible. So, and we don't necessarily have to go into extremes of AI alignment kind of reasoning that large-scale models necessarily going to be kind of evil and going to destroy the humanity. So I think it's a little bit premature to jump to such conclusions, but improving their ethical outputs, improving their robustness to distribution shifts, which was very important for AI safety, and kind of trying to develop methods that can detect changes in behavior, especially these emergent behaviors, can predict them well and perhaps steer in the desired direction. There are many open, interesting questions in this area. So I guess, yeah, I was not checking time, so please let me know if I'm over time already. But at higher level, with all this kind of recent joint collaborations with open source communities and different universities, trying to get more compute, essentially we trying to achieve and hopefully both capable but safe, robust, and aligned with human values, kind of large-scale general AI systems. And well, needless to say that on top of these foundation models, you can build multiple applications. You can fine-tune them for your specific domain. You can also apply them to various areas where data might be somewhat limited. A good example is, for example, healthcare, where you don't always have tons of data like text on the internet, but pre-trained model can help you boost your few-shot kind of generalization. And obtaining access to large-scale compute resources is quite essential for that. Supercomputers is one way, but also getting more funding from government or getting kind of compute from companies such as, say, Stability AI or something like that that all would be very helpful for development of open source AI models in that direction. So basically, yeah. And there is lots of interesting resources out there, and you're also welcome to check our workshops, our neural scaling laws that we were kind of teaching at UDM at Mill in the past 2 years. And also we have this series of neural scaling laws workshops with the next one happening at ICML in July, and hopefully the 5th one happening at New Rips in New Orleans this fall, end of November. Okay, thank you so much. And
thank you for that fabulous presentation. Right, we're going to try have Irina, that was amazing. Thank you so much. I certainly learned a huge amount there. That's really directly applicable to my life. So really happy. We've got a number of questions in the room and some online as well. We are running a little behind time. So if we could keep the answers maybe a little bit brief, Irina, that would be much appreciated. Thank you for that fabulous, fabulous talk. Right, first question is from Yasantha. Hi, Yasantha. Thanks for tuning in again today and for your questions. Do you think sub-symbolic generalization over multiple tasks will be the future of AGI? Is it possible to achieve AGI only by sub-symbolic?
Yeah, that's a good controversial question. But in a sense, I think it might be possible. I might be wrong. And the reason I think so is analogy with like our capabilities, our symbolic capabilities and so on. They somehow evolved by scaling biological networks, right? So in a sense, unless we believe in the creation or something, the evolution somehow started with single cells and scaled them to, well, biological organisms and to the brain. Somehow the symbolic capabilities became like emergent properties of this process, so to speak. So perhaps incorporating them directly into the model might be a good shortcut, just like inductive biases usually were always a good shortcut, maybe getting us there faster. On the other hand, again, with enough compute and data, I think it is possible to get to the point where capabilities may emerge. It would be interesting to see if that's the case. So.
Thank you. Thank you very much indeed. Next question online is from Paul Berger. And I think, Irina, you might also have this pasted to you in Zoom because it's quite long. Paul asks, thank you for your question, Paul. Paul asks, I would like to have Irina's point of view of cross-modality gains in learning. Some power law metrics in the pipeline, question mark. I mean, systems trained on several modalities at once versus separate systems addressing only one modality. The point is synergetic learning cross-modal should be more than the sum of individual unimodal contributions, but is there already quantified studies about this?
Yeah, that's actually a very good question because, I mean, multimodal systems are kind of proliferating there, and people approach multimodality either in kind of joined or sequential ways. So yeah, there are various models like this perceiver, uniperceiver, and so on and so forth that actually really try to train jointly on multiple modalities, but practical issue is that the challenge is it's not always easy to get all kind of modalities that are simultaneously happening in the same. So basically with video, that would be great, like with video models, because you will have your text and audio and images and video. But what is happening, sometimes you take two modalities, say like one clip-like models, text, image, you build a model with two modalities, and then if you have like text, audio, then essentially you can link the model sequentially. But yes, so you need to have like some common representation that can indeed like link, say, image to text, then text to audio, and so on. So Quantified studies, yeah, I mean, that's a good question. I'm not totally sure whether people really compared whether joint training on joint modalities would necessarily be better than doing it maybe like, as I said, sequentially or trying to transfer from one modality to another. So I'm not 100% sure that there is like a exhaustive kind of comprehensive quantified study of that. But still, what is quite surprising, nevertheless, that single modality training, such as language, shows quite mind-boggling levels of transfer to different modalities, as you're probably aware of, like this transformers, universal compute engines, paper, pre-trained language transferring to image. Well, of course, you need to adapt the input and maybe put adapters here and there, but seems like language models somehow manage to learn some concepts or representations that are generic enough that they can be transferred to image, or even better with decision transformers to sequence of decisions. So you give it like offline RL data. So that is quite mind-boggling. And I recently seen some paper, we're actually trying to see if we can reproduce it on larger scale. Can you transfer from language models, like purely pre-trained on language, to something like time series? Yeah, at least people were showing some promising results. And that is, to me, still mind-boggling how this transfer is happening, like what's in common. But yeah, so I guess to answer you back to your question, I'm not sure, and I think it would be a great study to indeed quantify if there is a kind of huge improvement in the kind of scaling laws and quality of the kind of results due to purely like simultaneous multimodal training instead of all this kind of sequential transfers.
Thank you so much, Irina. Brilliant answer and great question, Paul. Thank you. We've got a question here in the room for you. Let us know if you can hear okay.
Irina, thank you for your work. My name is Artem. I have a question about context size and capacity to increase context size for small language models like Red Pajamas, 7 billion parameters. And do you know how we can implement online learning for the attention-based networks?
Yeah, I mean, yeah, there is indeed huge recent advances in the large context, and Anthropic increased it to like 100K, right? And so on and so forth. There are various, okay, so kind of maybe better approaches to attention. That's kind of one thing people explore. Also, I mean, some notion of recurrence, like looking to like things like block recurrent transformers, perhaps. So yeah, so and in general, kind of some memory-based models. So I think there are multiple things kind of being explored right now. And honestly, yeah, it's very interesting question. I think it can be also, it can be done with medium or like relatively small size models, like the 7, 10 billion, 20 billion, not necessarily with kind of the top of the line, close to 200 billion models. Yeah, so I would probably need to dig a bit more into that literature, but I definitely know that it's like a topic of active work, and say on our Discord, conveniently called AGI Discord, where all these summit projects are actually taking place. Yeah, there are various channels, although not all of them are public anymore, but yeah, so there is ongoing work and people are exploring like what's next in terms of increasing the the window, the context window. So I think in the next year we will see improvements in that also in the open source models, pretty sure.
Thank you very much indeed, Irina. And do we have one more short question in the room? We have. From Zar.
Okay. Thank you for the talk. And I was wondering about these sort of quote unquote phase transitions when the model suddenly learns to do like arithmetic with larger digits. Could this be related to like greater depth of reasoning being unlocked with the larger models that like allow it to do more reasoning steps and thus solve the arithmetic problem?
That's a good question. Actually, trying to understand why specifically this type of tasks like arithmetic, like modular arithmetic, or this type of discrete kind of tasks, why they lend themselves, why this happens, why transitions happens with them and not maybe with any other task. That's a good question on its own. Whether it's a property of the model getting to like be able to do more steps of reasoning, or whether it's a property of the task. It's an interesting question. I mean, there are a few papers on grokking in the past year. We also hope to finally release ours, trying to basically look at the dynamics of solution and understand what patterns during kind of learning precede grokking, like what happens within the network that can be predictive about the fact whether transition going to happen or not. But I think it definitely relates to the properties of the task. And it may have something to do like with geometry of that kind of space or solution and geometry. I don't know. So basically, kind of trying to discuss it also with some people in math department. Yeah, because the structure of the problem, I think, is most important here for the fact whether the transition going to happen. Basically, it's a good open question. Yeah, right now, as I said, all we know, there are a few papers where people just try to see what changes in the solution dynamics and representations and so on seem to precede or be associated with such transitions, and how can you interpret them. Yeah, there are a few papers actually coming from, or already came out from MIT, Max Tegmark group, basically his students, and also from Jacob Steinhardt's group in Berkeley. Yeah, there was a clear paper, but yeah, they don't really connect those patterns with ability to do more steps of reasoning. It's a good question.
Thank you. Great questions, Zara. When I was wondering myself. Okay, folks, I think we have time for one more quick question in the room, just because our next speaker's just run out and he'll be back in 1 minute. So anybody want to take the last question for Irina here today in the room? No?
There was a question to give the link to AGI Discord. Just a second. It is on my homepage. So basically, it's right here. So there is a link. Yeah, there is a link to AGI Discord there.
Okay, fantastic. Thank you so much, Irina, for that really, really comprehensive and educational update. Big round of applause for Irina, please.
Thank you.